Okay, I needed to make a quick recording because we didn't have time to cover this, but it's because I was kind of spitballing today over what I thought was in this chapter, and I got 90. I had the 80% solution, except for a very important part, and that is most of the time things we rotate things. I mean, I spent quite a bit of time in class talking about how we get the change to that magnetic field induces a current. So the easiest way to do something is to rotate that magnet or to rotate the loop or whatever. And so I put on, and then another thing is, and this happens a lot. And in fact, um, uh, we're this thing in problem, and there's one other thing in problem three. Two formulas that you need to know to do two of the problems that I've assigned to you that might be a little bit tricky. So that we didn't cover today. So here we go. We've got a jet airplane, and this actually happens, and it really happens, and that's why the exterior of a jet airplane is very highly charged. As it's moving through the Earth's magnetic field, it's developing quite a bit of voltage as it's going through there, as it's going along. Another thing that creates a heck of a lot of voltage is a helicopter. In fact, when I was a young lieutenant back in the early 80s, one of my first units I was assigned to was a landing, what we call a landing support battalion, and our thing was to bring supplies into the beach and things like that. So, and one of the things we did was we brought in supplies from helicopters hanging from the bottom, these pallets and things hanging from the bottom of a helicopter. Well, what you're supposed when you hook those things up, the hook of the helicopter comes down. When the hook of the helicopter is coming down, you're supposed to hit that with a grounding rod because it's got a lot of positive, negative charge built up on it. Well, the Marines thought it'd be funny to tell the lieutenant, yeah, just whack it with your hand. It about put me on my ass. All right. Anyway, I was like, oh. So I was initiated into the unit. Luckily, I'm still here. All right. So problems 3 and 4 need some explanation, I believe. All right. So first of all, problem 3 is a little bit different in that it looks like this. So we've got a jet airplane is moving along, has a wingspan of 75 meters, and is flying at 265 meters per second. Okay. So what is the EMF what's the induced EMF between the wingtips if the Earth's magnetic field is 3 times 10 to the negative 5 Teslas, or 3, and that's about a Gauss. Okay, about 3 Gauss is the Earth's magnetic field. Okay, so here we go. Here's what's going on, and I had to load this thing here so we could get this, and this is what it looks like. So we've got an airplane flying. Here's its big wings. Here's the airplane. Okay, and it's flying along here. All right, so here it is, and it's 75. This length is 75 meters. Well, that's all fine and good. This is 75 meters going this way. Okay, now the Earth's magnetic field, we're going to say, is going in for lack of, and there's a uniform magnetic field that this is flying through. So look what's happening. It is moving over a magnetic field and it's changing it. Okay, so you might be saying, well, I thought with your ring it didn't matter. Well, it does. It does, because what's going on is behind it. We don't really have a conductor here. We don't have a conducting rod here. It's just moving through there. Okay, so it's always changing. So the magnetic field is always changing. All right, so that's going to induce a current. Now we learned, and then the EMF. We learned that today that the EMF is equal to the change in flux or the change in time. Well, here we've got a coil of n equals 1, so we don't need to put in the n. And so we've got, and I've got the magnetic field going in. It might be popping out. It depends on which hemisphere you're in, actually. And so it's moving along. And we learned that this is equal to B a cosine of theta. Well, it is the loop, or the thing is perpendicular to the magnetic field, so therefore the normal to it, theta is equal to 0, so the cosine of 0 is equal to 1. So we're off to a good start so far. But what is this B? Hey, what's going to change? Well, B is, which one of these over time is changing? I don't know. Well, yes, we do. It's the area of this rectangle that is changing. Okay, as it's moving along here, notice we basically have a rectangle that's always changing its area. So that's what's changing. The magnetic field's staying the same, but the area that it's moving through is changing. Okay? All right, so here we go. So we've got dA over dt. Now what's good? Now what is area? Area is equal to length times distance. Okay, times the x value. So we've got this length here, L. Here's my L right here. And then I've got this distance. Well, this is changing over time, dx dt, because it's got a velocity. And we know that the velocity is equal to dx over dt. So basically what we're doing is we're taking dA, this is a little calculus trick, we're taking dA dt is equal to L times dx dt, which gives me my velocity. So I've got L times v. And the way we write this is the EMF then is equal to B LV cosine 0. All right, so I had to, basically I told you how to do it, but that's it. All right, so there's that one. There's that problem out of the way. Now, the next problem that I need to explain, because we do so many rotations, all right, so is that it? Okay, we've got to look at 4 and 5. Yeah, because then the next two are transformer problems. Okay, so let's look at problems 4 and 5 real quick. Okay, so problem 4. Now, here's what we're doing, is we're rotating this coil. Now, right now, it's at a maximum, okay? We're rotating this coil. So what we're doing, and it's inside a magnetic field, okay? So again, we've got to get, did they give us the number of turns? Yeah, 650 turns. So I know this. What I'm going to be doing this time is changing the magnetic, because I know I'm going to get an EMF. All right, so just take a look at the picture. Then I'm going to go to my Ladybug here. Then I just had to install the drivers because I'm using a different computer. So it took a minute. So here we go. So we've got the EMF then is equal to the change in, once again, not doing the calculus too much, kind of doing an algebraic calculus thing. Again, it's equal to n. Well, you can change that to the negative too. All right, so what's changing though? The angle. Everything else is staying. It's not moving with a velocity. The area is not changing with a velocity like it is with the airplane. And it's what is rotating. Theta is changing. Okay? So the cosine is what's changing. So when I take the change in the flux over the change in time, I'm changing, and it's constantly changing. So therefore, it's a derivative basically. So what I've got to do is I've got this. I'm taking d of dt of, and we'll take the n to the outside because that's not going to change. Well, we're going to take n and b. We're going to take n. Gosh dang it. We're going to take n, the area, NB. I don't know why they don't make it the NBA, to the outside of this derivative. I apologize. We're taking the cosine of theta dt. Well, people go, well, wait a minute. You can't do d theta dt. Well, yeah, I can. I can change the angle. And the derivative of the cosine is negative sine theta. So it comes out to be negative sine. And the other thing we do is we say theta, because we're changing d theta dt, really, is what we're doing, because now we got to do the chain rule on the inside of here. D theta dt, the change in time or the change in angle is equal to 2 pi times the frequency. All right? There's the big, you just got a little physics 250 thrown at you here because we're not supposed to use calculus, but that's where it comes from. And some of you have taken calculus and you know that the derivative of the cosine is theta, but you also got to take the derivative of the inside because we're doing it dt. And because theta is equal to 2 pi times the frequency times time. Oh, that gives me my maximum when theta is equal to 2 pi or 0, f times t. You know, when f times t gives us a nice n-type number. So here we go. E max then is equal to NAB 2 pi times the frequency. And I think that will cover us. Let's take a look at this problem. We got B, that's going to stay the same. Omega is equal to 230, okay? Omega is the angular speed. Don't forget, omega is equal to 2 pi f. Oh, so now you're going, wait, what are you talking about? So omega is equal to 2 pi f. That's something that we talked about in physics 210 a little bit, but for the most part, there you go. All right. So let's go back and look again. Oh, they want us to do it in terms of omega instead of, so it's N A B omega. That's, so just put all these guys in a row and you got it. And then calculate the numerical value of V naught, okay? Now, problem 5, it says a coil, 500, N equals 500, A equals 2.25, and the Earth's magnetic field is producing an EMF of 12,000 volts, okay? At what frequency in RPMs must the coil be spun, okay? And we'll talk about part B later on. All right, so at what frequency must this, so a maximum EMF. So here you go. So you come back, so on problem 5, you got this going on. Problem 5, max EMF. E naught is given, is equal to NAB 2 pi times the frequency. The only thing they don't give you is this guy. You know everything else. Okay? All right. We're done here.